Hi, this is topic B.3 Gas Laws, and we're going to delve into some very important, very famous physicist laws here. Boyle's law, Charles's law, the Gay-Lussac law, and we're going to bring them all together to make something called the ideal gas equation. We'll also look at the difference between an ideal gas and a real gas. It's a great topic. For this topic, you are going to need the learning objective checklist. You need to assess what learning objectives you're really comfortable with in this checklist and give them a tick. And at the end of each section, I'll tell you exactly what to write in your revision note template. Okay, let's head into B3 Gas Laws. Kinetic theory sounds hard, but actually it's not. You basically have to memorise 6 sentences. Actual examiner feedback. Candidates had trouble stating the assumptions of the kinetic theory of an ideal gas. Well, do you know what? That is so simple because all you need to do is memorise these 6 statements. 1. The molecules are perfectly elastic. What that means is that any time a molecule has a collision within a gas, it doesn't lose any kinetic energy. 2. The molecules are spheres. In real life, we know they are not spheres, but if we assume they are spheres, to be perfectly honest, it makes our maths a lot easier. 3. The molecules are identical. Imagine you had a body of oxygen gas. You would then imagine lots of oxygen diatomic molecules bouncing around within this body of gas. In real life, it's practically impossible to have a pure gas. So not all the molecules would be identical. You might have some hydrogen in there or nitrogen. So we assume that the molecules are identical, but in real practice, they are not. With kinetic theory, we also assume that there are no forces between the molecules except when they collide. So this means that the molecules move with constant velocity between collisions. The 5th assumption is that the molecules are very small, meaning that their total volume is much smaller than the volume of the gas. Their volume would be negligible in comparison to the volume of the gas. If a gas meets all these assumptions, then what we can say is the gas is an ideal gas. The conditions under which a real gas acts like an ideal gas is when the gas is at a low pressure, a moderate temperature, and of low density. That is when a gas meets most of the kinetic theory assumptions. Okay, let's head to our revision note template. Write down the assumptions of kinetic theory in the other notes section of that template and then complete question 1 in B3 knowledge questions. Now, I know none of you are going to believe this, but recently I turned 21. No, I turned 40. And as a treat with me and my friends, who've been friends since we were at university, so that is 22 years ago, we decided we'd save up for a holiday and we'd go somewhere posh. So we went on holiday together and we had a right old time. And 2 of my friends decided they wanted to try diving. And part of their diving lessons, they talked a lot about pressure. And it, rightly enough, reminded me of pressure in physics syllabus because I'm that much of a sado, okay? But I'm going to explain pressure to you in terms of diving, and you're going to really enjoy it. Fluid pressure. Well, the first thing that we need to notice is that fluid can be anything. It can be gases or liquids. So I'm not just talking about bodily fluids. I'm not talking about fluids you might drink. I'm talking about fluids being gases, so the air around us, or liquids. Because they have fluid particles. That means the particles can move around. And when particles can move around, they can collide with each other. And when some things collide with each other, they exert a force. And when a force is exerted within a collision, it exerts a pressure. And that pressure is calculated using pressure equals force over area. Let's have a look at this lady diving. Say a little water molecule collides with the surface of her skin. It exerts a force at right angles to her skin. And if that force is exerted at right angles to her skin, that means the pressure is also in the direction of right angles to her skin.
So anytime you're in a fluid, the pressure is at right angles to the surface of wherever you are. So you can see we're looking anywhere here. She is experiencing a pressure at right angles to any surface in contact with the fluid. And we've got some rather nice little plants here in little test tubes, and you will see that there's pressure exerted on the water inside these test tubes, and they're all at right angles. What is pressure? Well, it has a formula. The pressure at the surface of a fluid can be calculated using the equation below, and we've got pressure as units of pascals, and 1 Pascal is equal to 1 Newton per metre squared. The force, of course, has units of newtons, and the area has units of metres squared, because if you look at an area of something, that might be 1 metre, that might be 1 metre. To calculate the area, you do 1 times 1, so you do metres times metres, so your unit of area is metres squared. And if you like using an equation triangle, we have an equation triangle here, where F is on the top. Of course, it's got a nice balloon here, and I thought it quite nice to show that the pressure on the surface of this balloon, due to the air particles or the atmospheric particles surrounding it, are at right angles. Remember, our pressure is exerted at right angles to the surface of whatever object we're looking at. When we think about a gas, we think about these particles, and they're randomly moving about. You can see them randomly moving about inside this container, but what you don't see here is they actually collide with the walls of the container. And that collision of the walls of the container is something that creates pressure. And specifically, usually 4 marks, there are 4 explanations for pressure in gases. The first mark always goes to the particles are in constant motion in random directions. So that goes back to here. These particles are in constant motion in random directions. You can see that. The second mark is that the particles collide with the walls of the container. And that makes sense. The particles collide with the walls of the container. The third mark to explain pressure in gases is that the collisions cause a force on the wall. And the final mark is that pressure is equal to force over area. What happens if we raise the temperature of this balloon? Say it's at 21 degrees centigrade and we want to raise the temperature to 30 degrees centigrade. Well, what it does is it speeds up the molecules or the particles. So these particles move with much greater speed, which means they have greater kinetic energy, and their internal energy increases as well. And then if you've got greater kinetic energy and they're moving at higher speed, they have more collisions with the sides because they're moving around much quicker and more randomly. And more collisions, coupled with the fact that they're hitting them with a faster speed, which means they have more energy and more force, means that the pressure on the sides is greater. So the effect of increasing the temperature of a gas means that the molecules speed up, or the particles speed up, but also the pressure increases as well.
I want to take a slight aside here because I think there's a derivation you need to learn. It's not confirmed, but I think there is. The data booklet gives this equation. It's P equals a third rho V squared. And what it really does is it shows that the pressure of a gas is related to the average translational speed of the molecules. So if the density of the gas remains constant, the pressure is proportional to V squared. The syllabus says that you as a student should understand from analysis that the change in momentum of particles due to collisions with a given surface gives rise to a pressure in gas. I think we've talked about that already, but I think there could be a derivation here. So let me walk you through this from first principles. I want you to consider one molecule of gas inside an empty piston. And what it's doing is it's bouncing back and forth along this length L inside the piston. When it travels towards the piston end, it has momentum mv. At some point, it will elastically collide with the wall and bounce back in the opposite direction, also with momentum mv. If we take the direction into account, we can see that the change in momentum is 2mv. And this means, using the relationship we found in A2, forces and momentum, we can find an expression for force as the change in momentum over the change in time, and that gives us an expression of 2mv over delta t. Let's take that further. I want you to think of the good old-fashioned equation speed equals distance over time. If we rearrange that for time, we know that time equals distance over speed. And we've got this information for the molecule. We know that it travels a distance of 2L, which is there and back inside the piston, and it travels at a speed of v. So the time taken for it to travel to one side and back again is 2L over v. And what we can do is take that expression for time and put it into the previous expression we had for force. You can see at the top we had force equals 2mv over delta t, and at the bottom, let's insert our expression for time. What we now have for the force expression is mv squared over L. Stick with me. Okay, we now have a pretty full expression for force, and we know, because we want to bring pressure into this derivation, that pressure equals force over area. So let's put our expression for force into force over area. And if you work through, you'll get pressure equals mv squared over v. That big V stands for volume, and we've got volume is equal to the area over the length of this piston. Now we have an expression for pressure, which is mv squared over v, volume. We need to try and bring density into this. And of course we'll know from GCSE that density equals mass over volume. And instead of using the m over v in the pressure equation, we can just insert density there. So now we have a much more compact expression for pressure, and it's pressure equals density times velocity squared. We're nearly there, but not quite. The expression we've got for pressure so far, which is density times velocity squared, only looks at us in one direction. We've got one axis of this three-dimensional space. And what we want to do is account for the pressure over 3 dimensions, not one. So that's why we add that factor of a third into there. So our final expression for pressure, as shown in the data booklet, is pressure equals 1/3 density times velocity squared. And that shows us that the pressure is directly proportional to the square of the average speed of the particles, and therefore the temperature of the gas. That's probably the hardest derivation I've come across in IB physics so far. I don't know if you're going to have to derive it in the exam. We haven't had enough exams to tell yet, but I suggest that this is one that would be good for you to memorise. Okay, head to your revision note template, write down what I've told you to write down on the screen, and I would also include the derivation for the formula we've just talked about. Next, we're going to look at learning objective B3-4, define the amount of a substance, and we're going to look at moles and Avogadro's constant. So, it all begins with something called Avogadro's constant. 1 mole of a substance contains the same number of particles as 1 mole of any other substance. So we define a mole as a certain number of particles in a substance. And the particles can be anything. They can be atoms, molecules, or ions. Now, we said it's a certain number of atoms. Well, that particular number is Avogadro's constant. And the number of atoms, molecules, or ions in 1 mole of a substance is called the Avogadro constant. Its value is 6.02 times 10 to the 23 atoms, molecules, or ions per mole, which is this big, huge number down here below. So in 1 mole of any substance, it has exactly that amount of molecules, atoms, or ions. Any substance. So if we look at 1 mole of sulfur, it has 6.02 times 10 to the 23 atoms in it. And if we look at 1 mole of sulfur dioxide, it has 6.02 times 10 to the 23 molecules of that inside it. So 1 mole has that number of molecules, atoms, or ion inside it, and that number is called the Avogadro's constant. The molar mass is how much 1 mole of that substance weighs. Now, why do we use a molar mass? Well, because the actual masses of atoms, molecules, and ions are too small to be useful in any form of calculation. So, for chemical amounts, we measure that in moles. And the mole is an SI base unit. We came across that in topic 1, measurements and uncertainties. It's a base unit, one of the 7 base units, and its symbol is MOL. The relative atomic mass is in grams is how much 1 mole of a substance weighs. So we know that 1 mole of a substance has 6.02 times 10 to the 23 atoms, molecules, or ions in it. But each substance will weigh a different amount, having that amount of atoms. So, for example, oxygen, 1 mole of it will weigh 32 grams, but calcium carbonate, the same number of particles, but will weigh a different amount. It will weigh 100 grams. Now, the number of moles, that's probably the easiest for us to measure the mass of a substance in. So we use the number of moles in a small n, and you can see that in the data booklet below, that we do see that small n number in 2 of the formulae. And we can calculate the number of moles when given the total number of atoms, that's the big N, in a sample of a substance. What we simply do is we'll say we've got a total number of atoms, let's say 12.04 times 10 to the 23 atoms. We divide it by Avogadro's constant, and that tells us how many moles we have, and that's a small n. So it's a very simple formula we'd use there first. Other example calculations involve calculating the mass of a substance when giving the number of moles and molar mass. So, for example, calculate the mass of 0.1 moles of iron, and we know that the molar mass of iron is 56 grams. Well, that's a simple ratio. N times 56 equals 5.6 grams. Okay, N is 0.1. So 0.1 times 56 is 5.6. Another example calculation would be you can calculate the number of atoms or molecules using the number of moles and the molar mass. So, for example, calculate the amount of water molecules in 36 grams of water. And we know that 1 molar mass of water is 18 grams. Well, 36 divided by 18 tells us that there's 2 moles of the substance there. So 2 times the number of particles in 2 moles is Avogadro's constant. So it's 12.04 times 10 to the 23 molecules. Really don't overthink this. It is basic maths, and the overriding concept is that 1 mole of any substance has 6.02 times 10 to the 23 particles within it, and that is Avogadro's constant. Okay, head to your revision note template and write down the definition for the amount of a substance and include Avogadro's constant in that definition. You'll probably want to note down a couple of the formula that we talked about in the last section too. So make sure that's all included, and we'll head on to the next section. In the previous topic, we were talking about molecular behaviour, and we were looking at a microscopic view of gas. So we're talking about the molecules. If we look at gas in another way, if we look at the macroscopic view, so looking at it as a body of gas from a bigger scale, there are only 4 main macroscopic quantities that can be varied within an ideal gas. If you take a gas and put it in a container, you can change the pressure of the gas, the volume of the gas, the temperature of the gas, or you can add some more gas or take some gas away, and ultimately what you would do is you'd change the number of moles of gas there. It's kind of important you understand how the ideal gas equation is derived, because it's made up of 3 different laws, gas laws in physics, that you will have studied in school. And the first of these laws is Boyle's law. I'm absolutely sure you've seen this in class. You've probably even done an experiment. And what Boyle's law does is that it investigates how the pressure of a gas affects the volume of a gas. Now, for that to be a fair test, we have to keep the other two of the 4 variables constant. So temperature and the number of moles of the gas have to stay exactly the same. To investigate this experiment, we would use equipment looking a little like this. We have a hand pump, which is used to increase the pressure to the volume of air inside this scale here. And what we find is that as the pressure of the gas increases, the volume of the air decreases. This volume here gets smaller. If you were to plot a graph, it would look a little like this graph up here. And we can see that the two are inversely proportional. P is proportional to 1 over V. If we take that a little bit further and look at putting that into a mathematical equation, we can then say that if you plot a graph of P versus 1 over V, we can see that they are proportional. That also means that we can come up with a mathematical formula at the end of P times V equals K, which is a constant. Let's keep this relationship in mind and look on to Charles's law. Charles's law is the investigation of how temperature affects the volume of a gas. To do that and to keep it a fair test, we need to make sure that pressure and the number of moles remains constant. The equipment you might use to investigate Charles's law is shown here. You would start off with some very icy water and have a column of air inside a capillary tube. You would measure the temperature of the water and note that down. As you heat the gas, you would notice that the volume of this column of air would increase. This tells you that as the temperature increases, the volume of the gas increases. So they are what is known as, in maths, directly proportional. You can see that we plot a graph of volume against temperature, and we have a nice straight line through the origin. In maths, you can say V is proportional to T, but you can also take that to another level and express the relationship as V divided by T is equal to K. Let's bear that relationship in mind as well and move on to the Gay-Lussac law. The Gay-Lussac law investigates how temperature affects the pressure of a gas. And to do that, to make it a fair test, we have to keep volume and the number of moles of the gas constant. You can see from this picture that as you increase the temperature of the gas, the molecules will move with a greater speed. They'll have greater velocity vectors. As the molecules collide with the side of the container, which is the property that dictates what the pressure of the gas is, those collisions will have a greater force. Thus, as the temperature increases, the pressure of the gas increases. Again, in mathematics, we can say that pressure is proportional to temperature. We can further relate that relationship down to pressure divided by temperature equals K. So we have 3 laws, each with their own mathematical relationship. If you remember, this was Boyle's law, PV equals K. This was Charles's law, V over T equals K. And this was the Gay-Lussac law, P over T equals K. They're all equal to a constant. So we can merge those 3 equations together. PV equals K, PV equals K. V over T, that was over there, V over T equals K. And P over T equals K. We're halfway to the ideal gas equation here. Those 3 laws have merged together to create a relationship. And we haven't included the number of moles in our relationship here, so I'd like to do that now. So we add in to the ideal gas equation the number of moles, which we've kept constant throughout, and ultimately what we've done is we've changed our constant into N and R, which are 2 constants found in the ideal gas equation. This equation is really, really important. You're asked to use it many times. If you use that equation in any form, either in the top form here or in the bottom form here, but you use degrees Celsius, your answers will be incorrect. It is really important that you convert temperature into Kelvin in all calculations. We have the 3 mathematical expressions for Boyle's law, and we have the final ideal gas equation. Write them down in your formulae section of your revision note template. Note the conditions. So, for example, with Boyle's law, pressure varies, volume varies, but temperature and number of molecules has to stay the same. I'd head to your graph section and draw graphs for each gas law, showing whether they are inversely proportional or directly proportional. And finally, head to knowledge questions and complete questions 2 to 12. This next learning objective of sketching and interpreting pressure volume diagrams is a starter into the higher level stuff in the next topic, but it's still in the standard level specification. So we're going to look at pressure volume diagrams in a little bit more detail now. If we think back to Boyle's law, we kept the temperature of a gas constant and the number of moles of a gas constant, and what we varied were pressure and volume. We drew a graph of pressure and volume and found that they were inversely proportional. And if you look at the bottom blue line here, that's the line you'd typically see when you think of Boyle's law. However, if you repeated Boyle's law with the same gas and the same number of moles at different temperatures, you'd see that line of inverse proportion move progressively up away from the axis. Each of these lines that I've shown on the graph, the blue lines, have the same temperature of gas, but as the temperature increases, each line moves progressively away. These lines are called isotherms. Iso means same, therm means temperature, same temperature. So if you're looking at a PV diagram, and one of the processes that that ideal gas is going through is that it increases in temperature, you can expect to see the isotherms stay indirectly proportional, but moving away from the axis as shown. When you think about an ideal gas, and we think about the 4 macroscopic properties, pressure, volume, temperature, and number of moles, there are transformations that can take place of that ideal gas. And when these transformations take place, work is either done on the gas or work is released by the gas. And there are 3 main types of transformations or processes that an ideal gas can undertake, and they can be represented on a PV diagram. So the first process we'll look at is isothermal. Isothermal means same temperature. That means a transformation is taking place within this ideal gas, and that gas is doing work or it's releasing work into the surroundings, but it's doing it at the same temperature. That transformation occurs at the same temperature. And that's called an isothermal process. And it's represented by following along the isotherm. So if an isothermal transformation takes place of an ideal gas, you will see movement along an isotherm. If the gas is isothermally expanding, then the gas is doing work and an equivalent amount of heat is absorbed into the gas to maintain the temperature constant. But if the gas is compressing isothermally, then the gas releases heat to the surroundings and it releases heat outside to make sure that everything stays constant. The next transformation we should consider with an ideal gas is transforming the gas but keeping the pressure constant. And those processes are called isobaric. Iso means the same, and baric, well, baric is a measure of temperature in the atmosphere, isn't it? So same pressure. In this isobaric process, the pressure remains constant. So if a gas changes state in an isobaric process, then to represent that on a PV diagram, the line has to go horizontally. Pressure is on the y-axis of a PV diagram, and to keep pressure the same number or constant, then any movement has to be horizontal. When the volume increases at a constant pressure, the temperature is also going to increase according to the ideal gas law. So that's why when you move horizontally from state to state to state and keeping an isobaric process, you'll notice that it goes up the isotherms, which means the temperature increases. And this process is typical in situations where the gas is allowed to expand or compress at atmospheric pressure. It will either increase in temperature or decrease in temperature, depending on how many isotherms it crosses in the process. The final process or transformation we want to consider in an ideal gas is an isovolumetric process, sometimes called isochoric. And this involves no change in volume. That means that any representation on the pressure volume diagram is represented by a vertical line where the volume stays constant. And you can see that by following that vertical line through an isovolumetric process, then the gas, as it undergoes this transition, is going to increase in pressure. And that vertical line shows the isovolumetric or the isochoric process. Any heat added to a gas at a constant volume will result in an increase in pressure, following the relationship that we found in the Gay-Lussac law. It's time for you to head to your revision note template, go to the common graphs section and draw those 3 common graphs for isobaric, isovolumetric and isothermal processes. In topic B1, we looked in detail at the concept of internal energy. I want to expand on this a little bit further by looking at internal energy of an ideal monatomic gas. Ideal gas is a gas that follows the kinetic theory assumptions, and a monatomic gas means it's only got one type of atom or one type of molecule. It's going to lead us into an equation that you'll have to use as part of this topic, and it's pretty detailed to get there, so stick with me in this last section of the tutorial. When we're looking at the internal energy of an ideal gas, we have to take the kinetic theory assumptions into account, and we have to assume the following. We have to assume that our ideal gas has a large number of perfectly elastic spheres moving in random motion. We have to assume there's no forces between the molecules. There's no work that needs to be done to change the position of a molecule. And what that means is that the molecules therefore have no potential energy. Let me repeat that. An ideal gas, when you're considering internal energy, has no potential energy. So what we'd previously said was a definition of internal energy was internal energy is the sum of both potential and the randomly distributed kinetic energies of the particles in a body. That's the internal energy of a real gas or of a solid or a liquid. It's not the internal energy of an ideal gas. Because there is no potential energy in an ideal gas, then the internal energy of an ideal gas is defined as the sum of the randomly distributed kinetic energies of the particle in a body. Can you see that I've taken out potential energy from that definition? This is quite often a thing that students would miss, and it's very key in, first of all, doing calculations of internal energy with real gases and ideal gases, but also just those simple marks and getting the definitions correct. In B1, we found an expression for the average kinetic energy of the molecules of a gas, and we found that it was proportional to the temperature in Kelvin. You'll remember this expression was the average kinetic energy, and that's EK with a little bar above it, is equal to 3/2 kT. But we want to know what the total kinetic energy of these molecules are, because when we're calculating the internal energy of an ideal gas, we're not looking at the average kinetic energy of the molecules, we're looking at the total kinetic energy of the molecules. So to adapt our equation for average kinetic energy into total, we have to multiply it by the number of molecules that are inside that gas. So you'll notice our lowest equation on the slide here is 1 mole of gas contains Na molecules. So the total kinetic energy is E total equals 3/2, and we multiply it by Avogadro's constant, kT. And that then simplifies down to 3/2 RT, where R is the gas constant and is equal to NaK. That means we now have an expression for the internal energy of an ideal gas, because an ideal gas is only concerned with kinetic energy. If you are ever asked to calculate or determine the internal energy of an ideal gas, then this is your expression. And we're finished B3. What I'd like you to do before we finish off completely is write down the definition of internal energy for an ideal gas in your revision note template in the definition section. Head to the equation section and write down the equation for internal energy of an ideal gas. And finally complete questions 13 to 15 in the knowledge questions. I'll see you in step 2.